All right, at this part of the course, we're usually going to focus on reactions with only one starting material. So here's a generic reaction with one starting material. This is the coefficient, like 1, 2, or 3, and this is the starting material. I'm just going to write it generically here. Okay, so here's a possible rate expression. Which order is this? First order. Now, so far, this is still the rate expression in terms of concentrations. So let's write this in terms of time. Now the rate expression would look like this. By the way, let's just make a prediction. As time goes on, would you expect the rate to increase or decrease? That's right. Why is that? Yeah, you're running out of starting materials. You would expect that the greatest rate would be at the start when you have the most amount of starting materials. Eventually, it seems like the reaction would come to a halt when you run out of starting materials, or maybe if you get to, if it's going to completion anyway. In any case, as the time goes on, the rate is going to be decreasing. Well, it turns out that our rate expression here now will be, well, have this equation. So this is the rate expression that corresponds to this. Notice that this was in terms of concentration, but now we've introduced time. We're showing how the time affects the concentration that we're going to have. So the rate doesn't appear explicitly in here. This is relating the rate to the concentration, and this is relating concentration to time. So if you're dealing with time, you probably want to use this approach. Notice here that there's this negative sign, which shows that when t gets bigger, oh, well, also, so as time goes on, what's going to happen to the concentration of our starting material? All right, and that's what this equation is really showing us with this negative sign. It's showing that the greater the time is, the smaller our concentration of A is going to be. All right, now this is what is called, as we talked about, the differential rate law. And this is what's called the integrated rate law. You guys taking calculus? Oh, no? Okay. Calculus a prerequisite for this course? Okay. So probably we don't need to go into this too much. But if you start with this equation and you take its integral, you could prove this equation. Or if you start with this equation and you differentiate it, you would get this equation. So this equation is the derivative of this one, and this equation is the integral of this one. Those are operations in calculus. That explains where these names came from. But even the book, I don't think, proves this. So I don't think you're going to be expected to prove this. You can just memorize this or look it up in a table. You don't get any cheat sheet, do you? So you'll have to memorize this probably. Okay, so this is something you probably do need to memorize. Now, let's say we were going to make a graph here. Well, we would use time as our horizontal variable. And what's our vertical variable going to be? The natural log of the concentration of the starting material. Now, can you guys see from this equation, what would be the slope of this curve? Negative k. Good. And what would be the y-intercept? That's right. So it looks like you guys are remembering from high school the equation y equals mx plus b. Okay. X, now we don't have x here, but x stands for the horizontal variable. Well, in this case, the horizontal variable is the time. And we don't have a y, but we have a vertical variable, which is the natural log of a. Notice that a is not the vertical variable, it's its log. That's the vertical variable. And b stands for the y-intercept. That's where you cross the y-axis. So how would I label this point? Natural log of A0. What does this stand for? This is the initial concentration. of the starting material. The 0 stands for the concentration at time 0. And we have to take its log. So if you could graph this equation, it would look like this. It would look like a straight line with a slope of negative k and a y-intercept of the natural log of the initial concentration of the starting material. So we have to keep in mind this is the vertical variable and time is the horizontal variable to interpret this equation. These are the things that are changing. Notice that time is a variable and the concentration of A is a variable, but everything else is a constant. K is the rate constant. This is a constant because it's just the initial concentration that won't change over the course of the reaction. It is whatever it was at the beginning of the reaction. All right, so we won't prove that these two equations go together. We'll just memorize that if you have this equation, you have this. So this would be called a first order integrated rate law because it comes from the first order differential equation. So this would be called a first order integrated rate law. It's not really obvious it's first order when you look at this. It's only because we know it came from here with an exponent of 1 that we would know that it's first order. All right, so if there's no getting around it, we're going to have to do a little math with logarithms. We better review some logarithm math that we'll need. So suppose we say that the logarithm of x is y. Anyone know what that means? Now, logarithms are exponents. So since this y is the logarithm, it must be an exponent. I just have to write down what the base of the exponent is. Well, natural logarithms have a special base, which is the number e. This stands for natural logarithm. Ln is the natural logarithm. Those have a base of e. So this means this, and this means this. These are two equivalent statements. They both mean the same thing. If you say the natural log of x is y, you mean that e to the y equals x. And we're only going to need natural logs for this chapter, so I'm going to stop saying natural log, and I'm just going to say log. But by log, I mean the natural log. Now, what would e to the 0th power be? We already talked about that. What does this tell us about logarithms? How could I translate this into a statement like this?
1 to the power, the natural logarithm of 1 equals 0.
That's right. So what this tells us here is, remember that the log is the exponent. So here the exponent is 0, so that's the log. This tells us that the log of 1 is 0. Okay, so these two things go together, and that's true for any logarithm. The log of 1 is always 0. Logarithms look like this. Notice that the log of 1 is 0. Also notice then, and as x gets bigger, the log gets bigger. And as x gets smaller, the log gets smaller. That's kind of intuitive. But if the log of 1 is 0, then the log of a fraction has to be negative. So this is useful to know about logarithms. The logs of fractions are negative because 1 is the dividing line. If you take the log of something bigger than 1, you would have a positive log. So if you take the log of something smaller than 1, you'd have to have a negative log. So negative logs are not mysterious, they're just the logs of fractions, fractions that are between 0 and 1. Also, notice that you can't take the log of a negative number. You can't take the log of a negative number. Why not? Because there's no power you can raise e to that would make it negative. It doesn't matter what power you raise e to, it would never come out negative because e is a positive number. So you can't take the log of a negative number. That's why I don't have a curve over on this side for negative x's. All right, so those are some important facts about logs. If you're trying to figure out the log of x times y, there's another way to write that. You guys happen to know another way to write the log of x times y? So that would be the log of x plus the log of y. This is an important algebraic fact about logs. The log of a product is the sum of the logs. The log of a product is the sum of the logs. And by analogy, we might be able to figure out the log of a quotient.
Oh, is it subtracting?
Yeah, the log of a quotient is the difference of the logs. We're not going to try to prove these facts. We should just memorize these facts about logs. Here's another fact. The log of something to a power is this. One of the useful things about logs is that colloquially speaking, they bring down exponents. When you take the log of something, it brings the exponent down. So this is another useful fact about logs.